We should understand. It's like setting sales, setting it's like it doesn't. It's just lost this level. It's just flashing.
And I asked them, when can I buy no, it was yes, so it's high speed, high speed. Yes,
Okay, folks online, can somebody confirm that you can see the slides here? You should be able to talk and I should be able to hear you. Yes, okay. Can somebody speak? I generally don't look at the chat. If you're online and you want to ask a question or answer a question, say something. So for now, could at least one of you come up? Hey, there we go. Okay.
All right, cool.
Thank you. What's your name?
Hi, I'm Avi.
Avi? Okay, thank you, Avi, for being the brave one to
No problem.
All right, and you can see the slides, right?
Correct. I think we're all good on the Zoom end.
Okay, good. Excellent. All right. So sorry I'm late. I'm actually surprised that this many of you are here today on this freezing cold day. I see some of you have like taken advantage of the online option, which is fine. But thank you for being here all the same, folks who showed up. So before we begin, we haven't gotten the assignment 1 stuff released yet. We need a mapping of you to your GitHub ID because we basically do all the submissions through GitHub Classroom. So we need to make sure that we have your correct GitHub before we sort of map all that out. So the TA has posted on Piazza. If you're not on Piazza, get on there. Basically, I think it's a spreadsheet or some kind of form for you to fill out so we can map your GitHub IDs to you so we can get this out quickly. My apologies is not out already. Other questions on logistics before I jump into things here? All right. Okay, so we finished off last lecture. Okay, so we were talking about graphics, right? We sort of gave, last lecture was mostly an overview of really? All right, so we were talking about graphics, okay, and like what GPUs sort of were originally designed for, which sort of informs why they're good at the things they're good at today. And the sort of biggest thing that GPUs were good at and designed for is drawing triangles. Okay, basically shading in millions and millions of little triangles, and you can do this all in parallel because the triangles are essentially they're not dependent on each other, right? Who's coded up the Ocean program in, pthreads or whatever, right? If you took 565, 437, I think we make you do it too, or at least look at it. When you did Ocean, what was the hardest part about Ocean? Communication, right? Like, so Ocean is like you're basically figuring out like heat transfer in an ocean. So you have like a certain temperature for each cell. And then you're figuring out over time, like how that temperature is moving. So if there's one hot spot of the ocean that sort of propagates along. And it's an iterative computation. So every iteration, the heat moves, in different directions, and eventually it sort of spreads out across the ocean. But the dynamics of how that works is the program. And you could do that in parallel. Okay, so you can basically have a big ocean and then cut it up among 4 processors. And each processor can sort of operate independently in all the parts that aren't the edges, right? Because it's like this processor is doing the upper quarter of the ocean, another processor is doing the bottom, the sort of lower right or lower left quadrant of the ocean, and so on. And where they sort of meet, you have to be careful about interacting, right? Because some of them are going to write to that temperature and need to read the temperature. And so trying to coordinate that and make the synchronization work is tricky. There's no synchronization in these triangles. Okay, it's like you're trying to do ocean, but you don't care about what all the other processors are doing. All you care about is how I sort of shade my own individual triangle. So it's really highly parallel. Some would call this, what would a computer science person call this problem? Embarrassingly parallel, right? Because, it's embarrassingly parallel because it's not hard to parallelize, right? For us, that's fantastic because that means that, we can get a lot of parallelism. For a computer science person or an algorithmic person who's trying to find the hard problem, like this is not a hard problem. It's embarrassingly parallel, like you're done. Like there's no research here, right? From an algorithmic standpoint, at least in terms of the parallelism. So this is sort of an embarrassingly parallel problem, and that sort of necessitated the design of the GPU, which was to have a whole bunch of parallel independent cores that could sort of run these shaders on all of these different parallel pieces. Okay, highly parallel, and you need a ton of memory bandwidth to do this. If you have a highly parallel computation, you have lots of threads trying to figure out colors. All of those threads need to read those colors at about, colors for the textures, etc., at about the same time because they're all happening in parallel. That means the demand on the memory system is huge. Okay, so you're going to have individual cores demanding megabytes of memory, and you're going to have tens of hundreds of these happening, and it's going to happen at the nanosecond scale, and you're going to end up with huge bandwidth demands. So as a result, what is sort of the bandwidth, the memory bandwidth in a common commodity GPU? What's a ballpark number of how big that is?
400 Gbps.
400 gigabytes per second. That's about right. Some of them are even more. I think H100s. Who's got the H100 number at the top of their head? Anyone doing machine learning? It's like 1.2 terabytes, right? So who's heard of high bandwidth memory? Maybe some folks. It's a stupid name, okay? Like we always do this, like, high bandwidth memory. And what happens when we get something higher? Well, we'll call it very high bandwidth memory. It's like VLSI, very large. It's like there's these sort of like, non-specific names that we give things. High bandwidth memory is a type of essentially DRAM-like memory, but it's not DRAM, okay? It's 3D die stacked, which means we put the sort of layers of memory on top of each other. We do a bunch of through silicon vias. It's a super wide interface, and you get super high bandwidth. Okay. The downside of HBM is actually capacity, right? Capacity is hard to get in HBM. That's why GPUs. You buy GPUs today. Any of you who've done this, you can't get like on a CPU. You can get like a terabyte or 2 terabyte worth of system memory. You can't get that on a GPU. 8 gigabytes is about the maximum today. So anyway, high bandwidth memory is what's employed in these things today to sort of feed the machine of needing all of these things read in parallel very, very quickly. And there's trade-offs with this. The more higher bandwidth you make the memory, the higher the latency gets. And those of you should sort of be familiar with this sort of difference between latency and bandwidth, right? Like latency is the amount of time it takes me to do one thing. Bandwidth is the number of things I can do per unit of time. And those two things are different, right? I can have a super high latency task. Like I can build a machine that has a huge latency, but it has super high bandwidth because maybe it does many of those high latency tasks at the same time, okay? So pipeline. Who knows what I mean when I say pipelining in a CPU core? Hopefully all of you. If not, reconsider this class. So pipelining in a CPU core, does it improve latency of a single instruction or make latency of a single instruction worse?
Slightly worse.
Slightly worse. Why? Yeah. Somebody else. Yeah.
Overhead from latches and stuff.
Overhead from latches, pipeline stages, right? If I don't pipeline my CPU and I just, have a single cycle processor, so 362 folks, like the thing you did, most of you took 437 at this point. So if you have a single cycle processor, the sort of signal flows through and you don't have to latch anywhere, right? You don't have to have these extra stages in the processor to sort of do the pipelining. So if you're just running a one instruction program and you add a pipeline, it actually makes the program slower because it takes longer. There's going to be more, there's basically more stuff in between when the electrons enter the processor and when the electrons leave the processor. But it helps what? What does pipelining help? Throughput of what? Instructions, right? Throughput of instructions, which affects the latency of the whole program, right? So when we're talking about latency and throughput, it's always important to, qualify what we're talking about, right? Like pipelining helps the latency of a program because the program can finish quicker by increasing the instruction throughput. But the individual instruction latency actually goes up. Okay, so whenever we talk about latency and throughput, you always have to sort of keep these sort of, the context in mind. Okay, questions on that? All right, hopefully this is like review for most of you folks. So this is an old picture now. This is some marketing slide from probably 10, 15 years ago. Just, to show you what a scene looks like. You've all seen the video game before, right? This, underneath all of this is a bunch of triangles, right? There's a bunch of triangles here, and then those triangles are essentially getting shaded in with all the different colors associated with this person's face, the background, his armor, the scars, all of this kind of stuff is sort of happening, by reading from textures and adjusting colors and projecting those onto the screen. Okay, so a very quick overview of what a graphics pipeline has historically looked like, and sort of where the programmability is in this pipeline. Okay, so over here we've got the frame buffer. Frame buffer is just a fancy graphics word for essentially an array that is all the colors on the screen. Okay, so if you've got a 1024 by 980 screen, then you've got 1024 by 980 colors, and depending on what your color depth is, right, like how many bits are associated with each color, that'll tell you how big your frame buffer is. So every 60th of a second, we're trying to write to this frame buffer, okay, to sort of tell us, what the next value of the screen should be. And then it sort of goes into the front. So the front end of this thing, and in this picture, the stuff that is fixed function is gray, and the stuff that's programmable is purple, okay? So the fixed, it sort of starts off by sort of reading all of these vertices. So trying to figure out what is inside the scene. Like I need to know what models my camera is capturing right now, and to try to figure out, what textures to read from and how to shade those things. And then there's a stage for essentially vertex processing, or vertex shaders, as this is often called. You can actually transform some of those vertices, so you can perturb things. You can do some kind of computations based on your scene, based on what the camera is, maybe based on time, if you're doing something like tessellation of water or snow effects or some kind of whatever. So the programmer is in there, able to write high-level graphics shader language code to perturb the vertices. And then it goes through some additional primitive setups, and then to rasterization and Z-calling. Who knows what Z-calling is? Anyone? Yeah.
Deleting the pixels that are behind an object that are blocked by text or 2D scene.
Exactly. So remember, we have a 3D scene. So there's all these 3D models hanging out in there. And then we have, a 2D plane that ultimately the scene needs to end up on. The viewpoint starts at the plane, which is the camera, and then it sort of goes out and tries to look at what's in the scene. Now, there could be stuff in front of other stuff that's in the scene, okay? And the sort of default thing to do is try to figure out everything that's actually in the frustum right now, actually everything that's in the scene, shade all of that stuff, but then eventually some of the stuff you don't actually need. Okay, so I don't actually need to run pixel shaders because maybe like that guy's face in the original picture, it's standing in front of, probably some other statues or something, right? And the triangles associated with those statues, I don't actually have to go figure out the color of those things because his face is in the way, okay? So Z-calling is the process of figuring out, here's all the triangles that are in my sort of view space, which ones are closest to the camera. And if something is completely occluded by other stuff that's in front of it, I'm gonna drop it. It's a little more subtle than that because of what? Like, let's say that I have something that's like right in front of the camera and then a bunch of stuff in the scene. What would make it so that I may still want to render and color the things that are behind the thing that's right in front of the camera? Transparency, okay? Like if there's a window, if my camera is right in front of a window, maybe that window is causing some, you have to color the sort of subtle, shading that occurs when you're looking through a pane of glass. It doesn't look the same as when you're looking normally, but you still actually want to render all the stuff behind it. So individual triangles can basically have this thing called transparency, which allows you to see the triangles behind them. So if the only way you call it off is if it's completely completely opaque, right? So if it's a wall standing in front of your camera, and then you've got that whole scene behind, I can just cut all the triangles for that whole scene behind and only render the wall because it's opaque, okay? It's kind of the idea. Then after you figure out what you actually need to shade, excuse me, you go into something called the pixel shaders. Okay, this is an older terminology. What's this called today often? What's another name for pixel shaders? Does anyone do any graphics rendering? Fragment shaders, anyone heard of that? That's sort of what pixel shaders have evolved into, sort of fragments or collections of pixels, not super important for this class, but basically trying to figure out programmatically what the color should be. And this is a process where we read these things called textures. Okay, so this guy's face, like this isn't generated procedurally at runtime. The artists, remember those guys that sat in the room at Electronic Arts, in addition to sort of making the robes, they make the colors of what the robe should look like. Okay, so there's basically these things called textures, which are, you can sort of think of them as .png files. They're basically just a file that's got a bunch of colors in them. It's more complicated than that. And they actually look super strange because they're in 2D space and then they get mapped into 3D space. I wish I had a picture of it, but if you looked at like the actual texture of that guy's face, it would look like a big fat man or something, right? Because it actually has to spray his whole 3-dimensional face out into a 2-dimensional plane inside the texture to because that's what ultimately gets read from. So this process is like, okay, figuring out what triangles I need, what additional computations I'm going to do to sort of perturb the look and feel of this texture. And why might you do this? Well, lighting is a big thing. Lighting can affect the color of the texture. Picture a bright light on a person's face versus darkness on the person's face. You want to have it look much different. As a result, the color is going to look much different. So you need some way to procedurally figure out what that is that you can't figure out statically when you're sort of drawing the person in the artist's studio, okay? And then once that's done, you go to this last phase called the ROP, which is basically then taking all of these and then projecting them onto the screen, rasterizing them into the 2D space so that we get the final bunch of colors, and that goes back out to the frame buffer, and you're sort of done. And all of these interactions between what we're calling the frame buffer here and these various phases, frame buffer is also what they call main memory in GPUs. So all of the stuff that gets loaded on a GPU, not just the actual frame itself, sort of lives in main memory. So at the beginning, you're sort of reading and potentially writing, to vertices, because these are all stored in memory. You're reading and writing potentially to textures in the texturing phase, and then you're reading and writing the ROP is ultimately putting stuff out into the actual frame buffer itself when you're done. And the key point of this diagram is to sort of notice these purple pieces. These were the pieces that were programmable. This is what you wrote programmable graphic shaders for. And before there was any such thing as CUDA, they started adding this functionality to make more and more complex vertex and pixel shaders so that you could do much more interesting things with your graphics. Okay, questions on this? Okay, so this sort of, yes, right here.
Why does the texture have to be 2D?
What do you mean? Well, okay, so it gets mapped into a 3-dimensional space,
Right.
but ultimately when you read from it, it's basically got X, Y, or UV coordinates, they're called, right? Again, it's just because where it sits in the 3D space is actually going to be dependent on the triangle, right? So what you really want, like when we generate these things, everything gets normalized to like a space of the model. So there is a ton of matrix transformation in all of this, because think about when you generate the model in the artist studio, it faces the camera, right? When you're sort of generating it, but then it twists, right, when it's in the real space. So then you have to then do a projection and translation of where the coordinates of all those triangles are in relation to where your camera is in the frustum. So there's many different transformations that happen here to sort of take it from one space to another. And these are all just matrix operations. There's a ton of math involved in trying to get from the sort of source rendering scene to the output. So why not 3-dimensional? It's sort of when the artist colors them in, it's in 3 dimensions. But then when they generate it, it just ends up being a 2-dimensional file. Again, I think 2-dimensional arrays are just kind of more natural in programming languages, et cetera. So, and when you visualize it, it gets mapped down to 2D. Because you need to define what that 3rd dimension is, right? Which is where the triangles come in. Does that kind of make sense? So you can sort of change the two things independently. So I can futz with the triangles, And then I can sort of shade them based on whatever color that would map to in a two-dimensional space. Yeah.
So how would this change if you were doing something like spatial computing and rendering scenes around the user instead of just in front of them?
What do you mean? So like if you've got
The pipeline.
like you're talking about something like augmented reality or something, it really doesn't matter, right? Augmented reality is just a screen with a different dimension, right? That wraps around. So you just have more pixels. Now, augmented reality has all of these extra computation tasks it has to do, like VIO pipelines, like figure out how your head is moving and how the scene should move, and like predict which way your head is going to move. There's a whole other depth of sort of more compute heavy computation that's not associated with rendering. At the end of the day, the rendering is still largely the same. They render it the same way you would on a video game. It's just that it's got more pixels. It's also stereoscopic, meaning they actually render two different things for the two different eyes. So they've got to do two scenes based on where each of your eyes are looking because you're so close to your face. And that matter, you're trying to like trick people into thinking they're in another world, right? You can't just have a flat thing. It actually has to have different perspective based on your eyeballs. There's weird, interesting things about predicting like which way their eyes are going to move and like which way their head is going to move because, what it's real. Like the world is, the real world we all live in is continuous, right? And when you're trying to digitize that, you have to do all kinds of stuff that sort of fake people into making them think it's still continuous. It's a lot harder to do and do well. Who's worn like an Oculus headset or whatever? Some of you. Is that still the latest? What is the coolest thing out there in like VR headsets?
Vision Pro is coming out next week.
Vision Pro, okay. When I first did it, I almost got sick. This was like 10 years ago. It also freaked me out. And it wasn't realistic. This was like probably 10, 15 years ago. Everyone knows what I mean by augmented reality, right? It's like, or virtual reality. I mean, everyone sort of knows. Augmented reality is I put something on my face, I look at all you guys, but there's like unicorns sitting in the back, right? Like stuff that's not real. So you take a real image and then you just render other new stuff into it. That's augmented reality. Virtual reality is there's nothing real, right? I'm in like the Middle Ages with holding a sword, fighting other knights or something, right? Yeah, anyway, that was what I did the first time I wore these things. And I got scared and almost got sick because it's sort of like, it's very foreign the first time you wear these things to sort of walk around in some virtual world. But anyway, the rendering is essentially the same, except there's a lot more of it, and there's a lot more sort of computation to figure out how to move the rendered image in ways that the user is sort of kept in the illusion that they're in the real world. Okay. Other questions here. All right. This is a little old now, but and this is sort of settled law at this point. Like the fraction of chips that are actually devoted to GPUs was growing for a long time and is now kind of settled down. So for example, you can't really buy a lot of CPUs today that don't have some integrated GPU part on them, right? Even if you go off and you buy your own discrete GPU for your PC, which people don't really do that much anymore. Like all the laptops today, all the laptop chips will have a bunch of CPU cores in them, and then they'll also have a GPU core sort of on the chip itself. And this was true, like these are older generations now. This is sort of circa 2013, 2014, where, this sort of fraction of the chip that was devoted to the GPU has grown. And I mean, today, anything you're interacting with, in real time, like a laptop or an iPad or a phone, the sort of core processing chip or at least the SoC is going to have a big chunk of it devoted to the GPU. So even if, you're sort of buying a CPU core, if you're going to interact with it, then there's the GPU on there. That's not true for data center class parts, right? That's why they have so many more threads for the CPU, because they don't need to render anything. They just need CPU cores to sort of, run your AWS jobs or whatever. Okay, so there's a little quiz online. You're sort of ready to take that if you're good to go. All right, so why use GPUs for computing? And this is a little counterintuitive to people at first, because when you think GPUs, what do you think about power? You think they're low power or high power?
High power.
High power, right? These things need like hundreds of watts. Anyone who's tried to build their own custom gaming rig or whatever, you have to buy a new power supply to feed these things. They're like hundreds and hundreds of watts. But the real advantage of doing compute on GPU versus doing it on a traditional CPU is actually energy efficiency. And yes, they suck a lot of power, but with all of that power, they're doing a lot more compute than the same amount of power, powering a CPU. Okay, so the difference between power and energy, right? Power is how much you take up given how much energy you use per unit time. And energy is how much is just the actual energy itself, right? So if you sort of integrated the power over the whole lifetime of a job, so let's say you have some super parallel job, and you launched it on a bunch of CPUs, they would run at a lower power, but they would run for a much longer time, okay? So the net energy that they would spend is actually going to be higher than the net energy your super power hungry GPU is going to use in a very short amount of time, okay? Which means that as a whole, GPUs are, and these are old numbers, but this still roughly holds true today, about an order of magnitude more energy efficient than traditional CPUs. And the reason for this is that they rely on programmer-defined parallelism. They don't have all of these energy-hungry structures trying to suck parallelism out of serial code. All of that control stuff just sucks energy, but doesn't, it maybe speeds the program up a bit, but not enough to sort of, overcome like a whole other thread of operations like you can get on a GPU. And they have a lot of stuff in there that's very highly targeted at latency, trying to make sure that those things come back very quickly. Trying to focus on latency means you have to spend power to do that, okay? And GPUs sort of give up on latency for the most part and focus only on throughput. And these numbers are real, okay? So what we did here to get these numbers is take the latest, again, they're gonna both be lower. We did this about 5 years ago. Take the latest CPU, okay? And you take what its peak compute performance is, okay? So most floating point operations per second if the thing was sort of fully used. So like a programmer has mined as much performance out of the CPU as they possibly can. And then for the power number, what is a good proxy for this in the industry? What would we use to figure out what the peak power of a chip would be? There's an acronym for this.
TDP.
TDP, which stands for what? Thermal design point, right? I think it's thermal design point. Thermal design power. Okay, maybe I actually can't remember what it is. I thought it was thermal design point, which is basically like, this is the maximum amount of power that we can put into this thing. Because if we try to put more power into this thing, it's going to melt, basically. So this is like maximum power consumption, TDP. So you take a max flops, okay, and a max TDP. So if I just was doing as much compute as I possibly could at the maximum energy this thing can consume, the most energy efficient sort of out of order CPUs will be about 2 nanojoules per operation if you sort of divided them out. The highest efficiency GPUs, and this has gotten even better, are 200 picojoules per operation. So like an order of magnitude less energy. And it's probably even closer to 2 orders of magnitude today based on the way these things have shifted. So the point of this is that if you have an application that has enough compute in it and has enough parallelism in it, and you can rewrite it to run on a GPU, it's an order of magnitude more energy efficient, okay? And energy is sort of king now when it comes to all processor design, right? We sort of hit limits in terms of how fast we can clock things, and pretty much every high-performance computing system is somehow limited by energy in some way. Yes?
I looked it up, it looks like both terms are either thermal design power or thermal design point.
Okay. What did you say? So you were wrong. It's better that you're wrong than I'm wrong, right? Like you're allowed to be wrong. I'm not allowed to be wrong. I am allowed to be wrong, but it's fine. So thermal design point or thermal design power. Yeah. Okay. Thank you. So it's kind of counterintuitive when I first show this because you think GPUs, you just think high power, and everyone just conflates power and energy unless you're a double E, right? You're like, yeah, whatever. They're sort of the same thing. No, they're not, right? Power is distinctly different than energy, and GPUs are actually way more energy efficient because because they don't waste energy on these other things that CPUs do to try to improve latency. Okay, questions on this? Now, this arrow is the hard part. It's what you guys are going to do when you write CUDA. Like, you actually have to get the thing to run on the GPU. And all of this assumes that it's running at peak performance, which is also very hard and impossible to do in some cases. So, this is sort of the high-level story, but as always, the actual, facts in the ground are a lot more convoluted than sort of just running everything on a GPU. So orders of magnitude, energy efficient, but it has to perform well, right? If you take a serial piece of code and put it on a GPU, this won't be true. The GPU will be way less energy efficient because it'll take forever to finish because it's just running one thread really slowly, okay? And it's got a lot of wasted power and all the other nonsense it's got inside of it that you're not using. Okay. All right. Okay, so at a high level, at a 10,000-foot view, what is the difference between a CPU and a GPU? So those of you who took 565, which I hope is most of you, sort of know what and if you took only 437, you won't have that much of an intuition, but maybe some. So a CPU is sort of like how we devote area, okay? Like this is a rough view of how much area is devoted to things. In a CPU, if you've got like a 4-core thing that's maybe sitting on my laptop, maybe 2 processors, 8 total or whatever, you've got a limited number of ALUs, a limited number of texts that are on that thing. Okay, 4, 8, 16, whatever. Then you've got a huge chunk of area devoted to control. And these are things like branch predictors, register renaming, all of this kind of stuff. And then the embarrassing thing about CPUs is that huge amounts of CPU area today is devoted to cache, right? Because the memory system is slow, right? This sort of memory wall that we hit 20, 30 years ago is a real problem. We're clocking, the individual transistors inside the CPUs at 4 gigahertz, but the memory can't keep up with that. So in order to try to, mitigate that issue, we have caches, right? We have multi-level caches. 565 does multi-level too, right? You guys who took 565,
Yeah.
right? L1 caches very close to the core that are super fast. They sort of get bigger and slower as you move out. And if you build a hierarchy and you actually have locality in your program, then you don't suffer the full latency of going to DRAM all the time because you're able to hit in your cache, okay? And you only have 4 threads, 8 threads. So if each, basically each of those threads gets a 4th and 8th of the cache, it usually works out, right? And a lot of, if you look at sort of CPU design generation to generation, a lot of what they've been doing is just adding more megabytes to the last level cache to try to, incorporate a bigger working set inside the cache. Because missing and going off chip to DRAM is just a disaster. In contrast, the GPU looks more like this. They have many, many ALUs, and they've been sort of arranged here in, what we'll learn is a SIMD fashion. Who's sort of SIMD before? Maybe a 565 touches on this, right? Somewhat. So vectors are a classic example of SIMD. GPU is basically a big vector machine where we've got a whole bunch of ALUs, very minimal control, very minimal cache. Okay, so if you look at the sort of the big block, the control, those of you who are colorblind, the control stuff is the sort of top part of that very first square, and the cache stuff is the very bottom part of that very first square, much, much smaller in relation to the amount of compute we've sort of devoted on chip. So this means that your caches are going to be largely useless in most programs because you've got a ton of threads and very little cache per thread. Okay. And that means you're going to have to go to DRAM a lot because you're not going to hit the cache. So you're going to suffer DRAM latencies. And what we're going to do to deal with that is just run more threads. That's sort of the idea. So this is 10,000 foot view of like core differences between CPU and GPU. Questions? Yeah.
So when you're writing a program on a GPU,
Yep.
Can you use locality at all? How do you take advantage of that?
Good question. So you have to take advantage of locality on GPUs because if there is locality in the program and you're just going to main memory every time, it's a disaster.
Yeah.
Okay. So in CPUs, what do you do from a coding perspective to take advantage of locality? What are some techniques you can do? Tiling, which does what? What does tiling do?
It's the working set into cache.
Puts the working set into the cache, right? 437 teaches this, 565 probably also, right? So like, if I'm stupid about my program and I just stream through huge amounts of data, caches are LRU, so you're gonna like load in a bunch of stuff, and then the stuff that you loaded in is gonna get kicked out before you ever reuse it, right? So you can do transformations on your program to make it much more cache friendly, so it fits inside the cache, okay? And this turns out to be probably the biggest thing that matters in optimizing CPU codes is making sure they're cache friendly. In GPUs, the cache is so small and you have so many threads, it's practically impossible to do that. So instead, the GPUs, they don't have a huge cache, but they actually have a scratch pad memory. They still have a reasonable amount of SRAM on chip, but it's not an on-demand managed cache like the CPU. It's an explicit programmer managed cache. So basically, like, picture a cache where you can say, instead of just like loading something and having it be in there the next time you try to reference it, where you say, put this thing in the cache. So like take A at 0 and put it inside the cache at element 0. And then every time I need A at 0, I go to this thing. And it will never be evicted unless I overwrite it. Okay. So you still have to take advantage of this locality, but it's not automated like it is in the CPU. It's now a manual process, but the nature of the problems and the nature of the programming model steers you to sort of use this scratchpad in an efficient way.
So that'd be if I wanted to store a texture that I was reading a bunch.
So textures, there's a caveat here for textures. Textures are special. They do have their own cache. But it's still relatively small, but the texturing, there's enough commonality there among the threads usually that it's okay. Compute and graphics are sort of totally different computing demands for the most part, okay, other than the fact that they're super parallel. But you as a CUDA programmer are going to have to explicitly fill your cache up. It's not a cache. So the difference between a cache and a scratchpad is what? Does anyone know the difference?
No coherence in scratchpad.
No coherence? Nah, yes, but go ahead.
Scratchpad is software control. Cache is
Right. Scratchpad is software controlled, cache is hardware controlled, which from a hardware standpoint, what does that mean? What does the cache have that the scratchpad does not? What do I need for a hardware managed cache? Looking for one word, 3 letters. Tag. I need tags, right? Because what does a tag do? If the cache loads something in, I don't actually know what address that is. I need an identifier. That identifier is the tag. So if you're having a dynamically managed hardware mechanism, you need tags so that way the next time the processor asks for an address and you go to look to see if it's in the cache, you're like, oh, is this address in here? You check the tag. You don't need a tag in a scratchpad. You throw away all of that tag overhead because now it's on the programmer. If you expected A0 to be in this block and you overwrote it with A6, your problem. Your program's going to be wrong, right? Like it's on the programmer now to explicitly manage the space. So it makes the hardware a lot more efficient. You don't have to deal with tags. You don't have to have associativity. You don't have to have all those things that you need when you've got a cache. But it makes a programmer's life more challenging because now they have to explicitly manage this thing. And GPUs do have both. They have cache and scratchpad. And as we sort of go through the architecture, you'll see how this works, but typically it's much more efficient if you use the scratchpad, and the scratchpads tend to be bigger, and the scratchpads have special features that they can actually share data among threads in a very efficient way. And as you go through the program model, this becomes clear how all this works. So if your program has locality, like matrix multiplication, this is machine learning, it's matrix multiplication for the most part, it has locality. If you just ignored all of that locality, it'd be a disaster on the GPU. So you have to tile your program appropriately and make sure the locality is captured inside of these scratch pads in order to make good use of it. Okay. Oftentimes, a lot of these programs don't have a lot of reuse, like a streaming program, for example, like vector add, right? Vector add, just take 2 big vectors, add them together, and compute the result. There's no locality there. There's spatial locality, we'll see will actually get spread across the individual threads, but there's no like reuse of the vectors because you just touch them once and write them out once and you're done. Right. So programs that are streaming, there's no sense in using a scratchpad or a cache because you don't reuse anything. Okay. Good question. Other questions? Yeah.
like cache hits on like a scratchpad if you're not using the tag.
Everything's a hit. If I ask for it, it must be there because you should have loaded it. So basically, the way you interact with these are loads and stores. And this is true of all scratchpads, not just GPU scratchpads. And so the scratchpad has its own address space. For the sake of argument, let's say it starts at 0. So if I do load 0 in the scratchpad, and I haven't stored to addresses 0 yet, it's just going to read out trash, right? If it's a secure GPU, it will have wiped the scratchpad, because otherwise you might be able to read whatever the last program put in there, which they all do today. But it will just give you back whatever is in that SRAM, and if you haven't stored to that location yet, you will get back nonsense, essentially. Okay, so everything is a hit. Every load hits, so there's no overhead in trying to figure out if it's hit or miss. There's no miss path because there never is one. But you better make sure that whatever you want is actually in there, or else you're screwed. Okay, good question. Yep. So yes, in the grand scheme of the whole GPU, since you can load generically from all the different flavors of memory, it basically carves out a portion of the virtual address space. So think about maybe addresses 0 through 8,000. If you access those addresses, it's going to get mapped to the scratchpad. It's like GPIO, right? Anyone who's done microcontrollers, maybe you think you're going to DRAM with a memory loader store, but you're actually getting redirected to go to the peripherals, configuration register or whatever. It's kind of the same thing, but you're going to get redirected to go to the scratch pad. Okay. Or there's explicit instructions that say this is explicitly a scratch pad loader store. Then you could just use the it's just zero-based offset addressing. Okay. Yeah.
Latency higher for that type of cache or like traditional?
What do you think?
I would expect it to be slow
You'd expect the scratch pad to be slower. Why?
because there's more like software overhead than just like get to it automatically at the hardware level.
So on an individual access basis, the scratch pad's going to be faster. Why? Why is the scratch pad going to be faster?
Because there's no tag management.
No tag, right? Think about building cache. First thing you gotta do is check your tags. Here, I know exactly what portion of the SRAM I'm going to is explicitly coded in the instruction. Now, from an overhead perspective, I had to have first done the store at some point, right? So I need to explicitly, so the way that this worked at the beginning was I loaded something from the global memory. So I did a global load. I put that in a register, and then I stored that into the scratch pad. Okay, and that process is slower than an on-demand cache where I just miss on the address and bring it in, because now I'm going through the register file, separate instructions, blah, blah, blah. But if you've got enough locality, right, the fact that you don't do a tag check every time and you read this thing 10, 20, 30 times, it amortizes out that overhead of the extra software instructions. And today they actually have instructions to explicitly just go straight from memory into the scratch pad, so you avoid the register file entirely. But your intuition is sort of right, but on an individual load basis, the scratch pad is better. Good question. Other questions? This is good. All right. Okay. So GPUs versus vector processors. So many of you will have heard of vector processors, or at least the vector elements inside traditional processors. Inside an Intel part, what are the vector units called? What are the vector instructions inside an Intel part?
MMX.
MMX, that's like 90s stuff. Yes, MMX is one of them. Remember, it's like multimedia extension. Look that up. I think that's right. No, you don't have to. MMX, I think it's multimedia extension. It was basically introduced. It was kind of, who took 565? You guys took 565. You talked about MMX, right? At some point? Okay. Now, some of you remember. But it's like, so MMX was like, okay, I had a 32-bit float. Okay, so I have a floating point operation, but let's say that I actually wanted that to be like 4 8-bit ins, because there were like 4 8-bit colors or something. So they changed the hardware so that way you could basically take your 32-bit float and then turn it into a bunch of 8-bit floats. So you had 4 times the throughput if everything was 8 bits. And they sort of extended that so they actually have true vector units that I think are 512 wide. I mean, they've got like 512 floats in each vector, and you explicitly encode these inside instructions inside your sort of normal CPU streams. You've got like your x86 instructions churning along, and then there's like a vector load instruction that'll load something into your vector register file, and then you'll do a vector operation that does it across all of the elements in the vector, and then you sort of store out that vector using a vector store operation. Okay, so vector, there used to be just purely vector processors. This company called Cray, who's ever heard of Cray? Some folks, right? It's still sort of around. AMD bought it at one point. They had these like very famous computers where, you could like sit on them. They were like, sort of had this weird, they were shaped in a big C, right, for the name Cray. Seymour Cray is actually from the Midwest. He's from this town called Chippewa Falls, I think, right in Wisconsin. So Cray had this big headquarters up there. I went to Chippewa Falls on vacation, not because Cray was there, because I was driving through. It's kind of a sad little town now because the company's not. But anyway, kind of a neat story. But they built these big computers, and they were basically vector computers. Okay, they basically had a bunch of these vector elements in them. They were super wide. And if you could program them, they were really good and really efficient at doing math. So what is the difference between this and a GPU? And, part of the reason is really the programming model, right? When you do vector instructions in a CPU, you have to explicitly vectorize things. So you have to have explicit vector instructions that say this is a vector-wide operation, okay? And usually you don't do this. The compiler does it for you. Right, so if you have this vectorizing compiler, if you use something like OpenMP, right, you can basically say this loop is data parallel. We'll learn what that is. If you don't know what it is, hopefully this lecture. And then we'll go and it'll generate all of those vector instructions for you. So you have to explicitly encode it in the instruction stream. In GPUs, as you'll see, you don't code in vectors. You write code sort of like single thread, right? You'll have thread IDs, but it won't be explicitly vectorized. the sort of stream of execution will be serial, and then behind the scenes, they're going to get grouped together into vectors. So this allows for crazy things like if statements and loops, where maybe sometimes some elements of the vector go one way on the if statement and other elements of the vector go the other way. If you're doing this in a vector processor, what would you need to do? Is this even possible? There's a word for this in a vector processor to do this.
Masking.
Masking, otherwise known as P. There's P. Predication. Anyone heard of this?
Yeah.
Masking, predication. Basically, if I've got a 32 wide vector, and I know that I only need half of the things in the vector to do a particular operation, I can have something called a predicate that says if this is 1, so basically it's 32 bits, right? 1 for each lane. And if the value is 1, you're going to do the operation. And if the value is 0, you're not going to do the operation. So when I go to do that instruction, I give it a pointer to a predicate register. It reads that register and decides which lanes do the operation. Okay, so you can do this with, x86. In GPUs, you don't have to do this. There's basically mechanisms inside the hardware to allow the different, lanes in the vector to go in different directions. And then they'll all come back together for you without you even knowing what's going on when you're coding the CUDA code. Okay. So you'll do this when we code things up in CUDA, and then you'll understand how it works behind the scenes when we look at the microarchitecture of how these things are built. So as a result, it's a lot easier. For as much as people complain about CUDA programming, it's a lot easier to program CUDA than it is to program these vector machines, because the programming model is serial, and then the system sort of takes it and turns it into this data parallel thing behind the scenes. Now, if you really want to squeeze every last ounce of performance out of these things, you usually have to understand what's going on vectorization wise, but you can get 90% of the performance with not really understanding much, right? Which is sort of the win. It's accessible for people to use these machines without having to be super expert, high performance programmers. Questions? Yeah.
The execution is still memory, right?
So the execution itself is what's okay. So they had different names for this. So there's this classification. Okay, so Flynn's taxonomy, right? Who knows what this is? No, we never talked about this at some point. So MIMD, SIMD. So like basically, MIMD is multiple instruction, multiple data. That's what a CPU is. Okay, so you've got a bunch of threads, they're all touching different data. So every time you execute an instruction, it's sort of, they're all independent. SIMD is what a vector is. Single instruction, multiple data. So I'm going to have one machine instruction, and then instead of just operating on one float, it's going to operate on 32 floats, a vector. Okay, that's SIMD. And so your question was really, is it still MIMD?
The GPGPU.
The GPGPU, so the programming model appears MIMD, but it's actually run on SIMD hardware. Okay, and so NVIDIA invented this term. So there's Flynn's taxonomy, which has been around since like the 70s. That sort of takes the M's and the D's and switches them around, right? And then there's what NVIDIA sort of came up with was this thing called SIMT, so single instruction, multiple thread, which is sort of like SIMD and sort of not. Okay, and the reason that this works is because the programming model looks MIMD, but then the hardware is sort of SIMDizing it. They also had another thing, SPMD, single program, multiple data. Okay, that's another NVIDIA-ism. They're kind of confusing. They were trying to like argue that this is sort of a new paradigm. Fundamentally, it's really a SIMD machine that you're running MIMD code on, right? And we'll sort of see that as we go through. Okay. You don't have to know that. This is just kind of interesting talking points. Here, other questions? Has anyone heard of SIMT before I brought up this slide? Okay, some folks. All right, so good. Please ask questions, okay? Because sometimes I assume you guys know things that you don't know yet, which is fine. All right, so how do we program these things today, at least by and large? So GPUs can't exist without a CPU. You need a CPU. It doesn't do well at operating system stuff. It doesn't do well at like accessing files. These are not super highly parallel tasks. So you need something to do all the management. And they're always coupled together today with some CPU. In CUDA terminology, they call this the host. Like the CPU is a virus or something. It's bolted onto the, or the GPU is a virus and it sort of bolted itself onto the host. So the host does all the orchestration, okay? It opens files, it sort of puts stuff into the GPU, it kicks off the GPU's work and then sort of reads stuff back out. And the sort of general flow of things is that you'll have a big bunch of work. The CPU will go off and collect all the stuff it needs for that work. And then it will spawn work to the GPU. Okay, the GPU will go off and do its thing, and then when it's done, it'll tell the CPU, and then it will read the results back out of the GPU and then go do something else. You can continue to do stuff on the CPU while the GPU is doing things. This happens in some programs. It doesn't happen in a lot of programs. Why? Well, because if you spawn something on the GPU, unless you have something different to do on the CPU, you're usually better off just doing all the work on the GPU in the first place and just having the CPU hang around. Now, there are some programs where this is not true, and there's some work in like system space on trying to figure out, what's a good way for these things to communicate and handshake, like we're sort of wasting the CPU if it's waiting around for the GPU. But certainly for things like machine learning, it's going to queue up a bunch of kernels. It's going to handle the admin stuff, but you're not going to run the gems on the CPU because it's just so much efficient. So the CPU is going to just sit around waiting for the GPU to tell it it's done, sort of orchestrate the back and forth. Okay. So there's this sort of explicit phases here because generally you need a big bunch of work to kick off the GPU. It takes time to kick things off. It's not instantaneous. Even in these integrated parts, it's still an overhead to do this. So you need enough work to sort of justify sending it over to the GPU and then waiting for things to come back. Okay. So the way that this worked in the early days is you had to explicitly manage the memory. So I would load, think about any program you've ever written. Where did it get its inputs from? Well, you either like randomized a matrix or something, or you read something from disk, or you took user input or whatever, okay? That stuff lives in the CPU. So even if you're doing like a gem, you're probably opening a file to read the source for the matrix multiply. So gem stands for general matrix multiplication. So I'll say the word gem a lot because that's a very important workload. You have to read in the inputs, okay? And then you take that thing and then you had to explicitly say, memcopy, right? It's like memcopy on a CPU, except now instead of going from one location on the CPU to another location on the CPU, I'm going to memcopy into the GPU memory space. And then after that's set up, you sort of pass the GPU the pointers to the things that you put in GPU memory, kick off the kernel, it reads from those pointers, it's done, and then you read from some output pointer and copy the stuff back to the CPU. That was the way it was typically done. There are now much more friendly ways to do this. So there's this thing called unified virtual memory. So the CPU and the GPU actually share the same address space. They have, if you're using a discrete GPU, they still have different discrete memories, okay? So there's different ways to sort of bolt CPUs and GPUs together. The way that's the most efficient from the GPU's perspective is discrete, meaning that it's a whole other part with a whole separate memory system. And the reason for this is that the demands of the GPU's memory system are much different than the demands of the CPU's memory system. If you try to bolt them together to the same memory system, you're going to screw one of them, right? CPU needs big capacity, low latency. GPU needs high bandwidth. And those things are in collision with one another. So the way that this still works this way today, like you buy a GPU, it only has a certain amount of memory. That's because that memory is highly specialized for bandwidth. And if we tried to bolt it onto the CPU's memory and have that be the only source of memory, you wouldn't get the bandwidth you needed, or you just kneecap the CPU in terms of latency and capacity to give it a high bandwidth memory. Okay, so that's the way that sort of high performance systems are designed. Lower performance systems, like the GPU that's in here, they will share the same memory system. Okay, so they'll have the same like GDDR. Well, on the laptop, it's like LPDDR4. 3, it's probably still 3. LPDDR what? What's the latest LPDDR?
I think it's
Is it 5? Oh man, I gotta keep up. So LPDDR 5, whatever. So there's all these. Who's heard of JDEC? Some folks. So have you ever wondered where the term like LPDDR or HBM came from? Maybe not really. Okay, it comes from this standardization body. We'll study DRAM a little bit in this class because understanding how DRAM works is actually kind of interesting in context of GPUs, but there's this thing called JDEC, which basically specifies the timing for all these buzzwords that you've heard about. DDR5, DDR4, GDDR, which is graphics DDR memory, HBM. These essentially boil down to like a set of standards and timing so that DRAM manufacturers can make something, and then the CPU manufacturers can know how to build the memory controller that works with that thing. Right, because these two industries are sort of separated, right? Micron and Samsung to some extent these days are sort of going off and making memory chips, and then the sort of compute companies are just making the compute chips, and they need to talk to each other. And that interface is defined as something called JDEC, and these sort of buzz terms that you've heard, like LPDDR5. What does that mean? You can go look up what that means. You can sign up for JDEC and get like a 60-page document that says what the specs for LPDDR5 are. And then basically the CPU companies can use that to build memory controllers to interface with these different types of memories, okay? So anyway, if I try, the GPU that's on this thing that is sharing the memory space with the CPU, they both have to use the LPDDR5 memory, which is part of the reason why this thing won't run like high-end games quite as well, right? Because it doesn't, the discrete GPU has HBM memory, which has way more bandwidth than LPDDR5 memory, okay? Anyway, questions on this? Yes.
Do APUs also have separate discrete memory?
APUs have the same memory. So that's sort of, when AMD came up with this term APU, which is Accelerator Program Unit, I can't remember, I think this is the acronym is. Yeah, don't check me on that. Excuse me. That was the sort of shtick, was that like you bolt the processor and the CPU cores together and they share the same memory system. This is nicer because there's no mem copies, right? And intuitively, that should be like, no mem copies better, right? But no, not really. You're better off copying it into a more high performance memory and then copying it back than living with the low performance memory. If all you care about is sort of GPU throughput.
Is all that like other overhead that comes between going to CPU to GPU, is that diminished in the APU?
Yeah, because they're more tightly integrated. When you go CPU to GPU on like a typical PC, you go over PCIe. PCIe is slow. Okay, it's an I/O interface. Even the express and multiple lane PCIe's have relatively high bandwidth, but nothing like on-chip bandwidth. Okay, so it is quicker to communicate spawn kernels, et cetera, if they're integrated. But the downside is usually the GPUs are smaller because they're bolted together with the CPU, right? So their power envelope is cut in half because they have to devote the power to the CPU, and they can't use the sort of high BP memory system that the GPU can. Okay, good. So if you had a bunch of really small kernels that didn't have a huge memory demand, you might be better off on an integrated part. But it turns out those ones are pretty good on CPUs already. So that space of like doing compute in the integrated space, it has a space certainly in SoCs and things like, VR, AR. There's maybe an argument for this, but in terms of like churning out matrix multiplications to do machine learning, you're better off with the discrete part. Okay, yeah.
What about what Apple is doing these days? Putting an entire desktop plus GPU on an SoC.
Yeah. So that's sort of an in-between, right? Now, I don't know precisely what the memory system configuration of that is. So Apple is kind of this weird animal, right? It's its own beast. You don't really know anything about what Apple is doing. They don't release much publicly. NVIDIA is not much better, but at least the compute stuff is more, I don't know, like CUDA is very well managed, right? To do compute on like an Apple GPU, you have to use OpenCL, right? And OpenCL is like it's meant to be an open standard that's supposed to do compute. Ideally, this was supposed to be the holy grail of like you write everything in OpenCL and then it will run on any accelerator. Okay. The problem with this is that it's sort of like people have compared it to like a dysfunctional democracy fighting against a super efficient authoritarian regime, okay, where the dysfunctional democracy is OpenCL and the authoritarian regime is NVIDIA, okay, because CUDA, NVIDIA owns, okay? NVIDIA owns and it only works on NVIDIA machines. So you can run OpenCL on NVIDIA machines, but they put zero effort into making sure it works well. And then they add new features and do whatever they want in the CUDA space to make it much, much better. And then OpenCL just kind of hangs out and yeah, it kind of runs, but you never actually choose it because the NVIDIA stuff is highly supported and better, and only they do it. So, why would I sink money into this open standard that is going to allow my competitors to sell parts when I can like wholly own my own thing and then take away all their market share because you can only run it on my systems, right? Like in practice, unfortunately, capitalism is brutal, right? Like these kind of things that seem like, they're good ideas on the surface, like aren't, because there's like perverse incentives for people to completely break the system. So OpenCL is there. If you want to program Apple machines, you have to use OpenCL. I think you can use Vulkan too. It's another sort of more open, lower level interface. And to be honest with you, I don't know precisely what the head-to-head is of the sort of the beefy GPUs that are inside this thing and a discrete NVIDIA GPUs when it comes to graphics.
Because there's definitely a lot of overhead involved with the integrated GPU.
Yeah, no, definitely. I mean, overhead in what sense?
Coherence overhead.
Right. So if you want to keep the caches coherent, yes. I mean, a lot of times they handle this by just like having caches, but having them be incoherent, right?
Also, it depends on if we have the same physical memory or
Right.
if we have different physical
Right.
memory but same logical abstraction.
Right.
Whereas I think in Apple's case, it's all shared.
Right. So the physical memory is shared.
Yeah.
I believe all integrated parts have shared DRAMs as well, and that's true for Apple. I mean, that's just simpler, right? They go to the same memory controller on the same chip. Otherwise, you have to, if you think about the system design, right? You'd have to have like separate memory controllers going to separate memory substrates. You could do it, but is it a win? I don't know.
And then I think another question
Yeah.
is how big the cache block is. So,
Right.
for example, for many GPUs, it's either 128 bytes
Right.
or 256 bytes,
Mhm.
and for many CPUs, it's 64 bytes.
Right.
Whereas for the Apple stuff, they're just using 128 for everything.
Right. So again, and that's maybe hurting some CPU workloads,
Yeah.
right? So I don't know. I don't actually know enough about specifically what's going on inside these things to comment really intelligently about it. But these are the trade-offs that you sort of run into when you start bolting these two things together. Different demands, different memory hierarchy, coherence becomes a mess. We'll study that a little bit in the integrated side of this class. But typically when they do this integrated parts, the main market for that is still graphics for the most part. Even when you're talking about an integrated SoC for like VR, AR, right? And you've got all these different discrete accelerators for all the cool things you want to do for AR, VR. They usually just use the GPU only for graphics because it needs to render the screen, right? And it's good at that. And then they don't worry about, all the other accelerator pieces are sort of their own custom things. Anyway, okay. All right, so SIMT execution model. So warp. So there's this term called warp, which maybe some of you have heard about before, okay? So the SIMT model is that the programmer sees MIMD threads, so I'll say scalar threads a lot in this class. That basically is sort of like a CPU program, where you're sort of going through the code like in a serial manner, and you don't really know what your sort of peer threads are doing, okay? So when you cook things up, you're gonna cook things up in respect to one thread. Underneath that programming model, the GPU is going to butt things into what's known as a warp. Okay, a warp is kind of this cool word. What do you think of when you hear warp?
Warp speed.
Sorry?
Warp speed.
Warp speed from
Star Trek.
Star Trek. Who's heard of Star Trek? Some people haven't heard of Star Trek. All right, that's fine. I mean, it's getting old now. Are they still making Star Treks? There's like new ones? Okay, anyway, I haven't watched a long time. Anyway, it's kind of a cool word because it sounds fast, right? Pop culturists have turned this into this fast thing. But it turns out that it actually has a meaning in the textile world, okay? And that's the much more boring meaning that the NVIDIA warp comes from, which, you don't really think about that. You just think of fast, probably. It's basically a collection of threads, okay? So when you're sort of weaving things together, and I don't have a great explanation of this, you can go to the wiki page if you really want to learn how this machine works. But essentially, you've got a bunch of threads that you're trying to weave together into some fabric. And then there's this big fat thread called a weft, and then you put a bunch of little threads, which are going to be the end fabric together, and then sort of collections of these are known as a warp, okay? And why does that matter for GPUs? A warp is going to be a collection of threads. Okay, it's going to be a group of threads that are sort of together. And that's where the term warp comes from, and it has this positive side effect that it also sounds really fast. NVIDIA doesn't, or AMD doesn't call these things warps because, I don't know, because we couldn't all agree on anything. So they call them wavefronts, but they mean exactly the same thing. It's basically you're going to group a bunch of scalar MIMD threads together into an execution unit, and AMD calls these wavefronts. Now, the granularity at which you do this is machine dependent. Typically and historically and still today, NVIDIA groups theirs together into collections of 32 threads. AMD's is a little bit wider. They group it into 64 threads instead. What do you think the trade-offs are between making the warp wider or smaller? Just without really knowing anything, what intuitively might you think if you're sort of packing things together in bigger or smaller granularities? Yeah.
Let's have more things that are able to be run in parallel.
More things in parallel. So which one do you think would be more efficient for, very, very regularized operations? 64, right? 64, the bigger is better, right? Because I'm amortizing more of that control overhead across more of the threads. What's the downside of going big. Yeah. Control flow divergence, which is a fancy term that we'll get to later, which basically means that like, okay, that's all great if they all go the same way, right? I get a 64 times amortization across all of these things on every instruction. But if they don't all go the same way, like if I have a big switch statement and then all of them go 64 different ways, I still have to run that on a 64 wide machine, right? And what is that going to mean? So like I have 64 lanes in my vector, but only one of them is actually going through this code path. So what will I have to do?
Mask 63.
I'll have to mask off 63 of them and just run one thread. So I've got this super wide machine. And then I'm going to say, okay, but I only want one. I only want one. The rest of them are going to sit there and they're going to do nothing. And it's even worse because if one of them went this way, 63 of them went in 63 other directions. So after I finish this one, I have to go to the next one. And that one's also going to run at 1/64th. And you serialize all those paths. And now any benefit you got from going on a GPU is totally hosed, right? So the smaller you make these things, the more adaptive you can be to these sort of more complex programs. Okay, so historically, this means that AMD GPUs have been more efficient at graphics. In fact, the hardware itself usually has been better, even though NVIDIA has been like outperforming them from the graphics market standpoint for a long time. The hardware has been arguably better than NVIDIA's hardware, more efficient, but the software and the marketing on NVIDIA's side is just sort of outdone AMD. I mean, gamers still buy AMD parts, so usually better price point wise, especially today with all this sort of hype on driving up GPU prices. Okay, so this is a warp. And the general idea here is you got scalar threads and you're going to group them together for execution on a wide machine. All right, why warp textile industry? All right, that's the first lecture. Let's very quickly start the next one. Questions so far? All right, let's go to. I prepped for like all the way up to slide set 4 today, but I finished only one. All right, so let's talk about this parallelism a little bit. So this slide set is going to go through parallelism in general. You sort of know something about parallelism. What is the parallelism that we're going to exploit on this GPU? And this sort of drives what the programming model of the GPU looks like. Then in addition to that, we're going to introduce CUDA-C. So you're going to see some programs. You're going to see how you actually run things on GPUs, because you're going to be asked to do that in your project. Obviously not by the end of today, but by the end of this lecture, you should basically understand a simple vector add program and be able to code this up without the slides, like by yourself in a couple of hours or less. All right. So let me just do a little bit about this. So parallelism in general. What are some types of parallelism? Yes.
Task level
parallelism, which would generally mean what?
That would mean you break up a process into different tasks and then give them to different clusters, different CPUs.
So what's an example of task level parallelism? A concrete example?
Like a web search.
Web search, right? Apache server. Like basically you have things coming in and then you're trying to service all of these tasks in parallel. That's one. And again, this is sort of subjective definition, right? There's no like Bible of this is all the levels of parallelism. They're sort of used in different ways. But what are some other examples of parallelism? We talked about a couple already in this class. Instruction level parallelism. This is when you've got a serial stream of instructions and you're trying to basically run them in parallel, either through pipelining or through out of order execution, etc. ILP generally it's called. What's another one?
Data level.
What's that?
Data level.
Data level parallelism. That's what the GPU is going to exploit. We'll talk about that. And thread level parallelism is another big one, right? That's the Ocean program, right? It's not really task level parallelism. You're still sort of taking this sort of big program and cutting it up into threads. It's not precisely data level parallelism because it's a little more fine grained. There's an even finer grained level of parallelism that VLSI folks may be aware of or think about. Bit level parallelism, right? Like basically doing things across multiple bits at once. So there's a few examples here of different types of parallelism. So instruction level parallelism we've talked about. That's what out of order CPU cores are going for. Task level parallelism is more like breaking up a program. Or sorry, task level parallelism is more like processes or, data center services, et cetera. Bit level parallelism is trying to, do more bit level computation in parallel, like trying to basically do carry look ahead adders, for example, where you're trying to like do a bunch of stuff at the very lowest level of the computation more in parallel. And then finally, this thing that we're really going to focus on, and there are other definitions of parallelism. These are just some examples. Okay, the thing that GPUs leverage is this thing called data level parallelism. Okay, which is defined by having identical computation just across different data. So if you data parallelism, think vector. Okay, of one single machine instruction that's going to operate on different specific pieces of data. Okay, the Flint's taxonomy for this is known as single instruction multiple data, or SIMD. You'll see this a lot. So instructions these are the individual instructions that exploit data level parallelism. And then NVIDIA invented this term called SPIMD, single program multiple data. And that is sort of what your kernel is meant to be. You're going to write these kernels in this class. They're not individual instructions. They're kind of whole programs, sort of. They're like little parts of programs. And you'll sort of write them in this way. There's going to be one program that's going to operate on multiple data, and you're going to access that data essentially with thread indices. Okay. And GPUs are designed specifically for this for several reasons. One, at their very core, they're vector engines. They're amortizing across the threads. And they also need high regularity in their memory accesses. To get that peak bandwidth, that terabyte worth of bandwidth, you can't be accessing stuff all over the place. Memory systems are not built to handle that well. They are built to handle contiguous accesses to data. Okay. And if you write things in this data parallel way, you will very naturally have side-by-side threads in your big grid of threads access side-by-side pieces of data, which will allow us to aggregate that up to the memory system. So we sort of see very wide accesses, okay? Which means we can suck up that memory bandwidth as much as possible, because that's really, what's going to keep the thing fed, okay? Questions on this? All right. I'm done. I'm over time. We'll come back and we'll keep going today. Look for Piazza if I want to speed us up, because I definitely didn't go very fast today. I will announce by the end of the day if I want you guys to read anything before or watch anything before the end of the next class. And if I do that, I will ask for questions and then just go very fast through a few slides and then stop. Okay. All right. Thank you. I'll see you all on Thursday. No office hours today. I have to move them to Thursday. So it'll be Wednesday, Thursday this week, 1:15 to 2:15 if you want to come talk to me. Okay. Thank you.
I had a quick question.
So for the